Over to you, Dr. Jiffin.
Thank you very much.
Yeah, thank you, Dr. Rajesh Baby. So a very good afternoon to one and all who gathered in this meeting. So with great honor and pleasure, I would like to welcome Professor Stefan Maas for this keynote session. He is currently working as a professor in the Department of Engineering at the University of Luxembourg. Professor Stefan has studied in mechanical engineering with a specialization in theoretical engineering at University of Kaiserslautern, Germany, and completed PhD in dynamics and controls in the same university in 1991. Professor Stefan has expertise in various research areas such as applied mechanics, strength of materials, finite elements, biomechanics, renewable energies, energy efficiency in buildings, and industrial processes. Professor Stefan is having more than 100 publications in the peer-reviewed journals since 2006 and completed more than 20 PhD theses as a principal supervisor. He has received many externally funded projects by various industries and European institutions. Today, Professor Maas will handle a session on the energy efficiency of buildings. So once again, I would like to Professor Stefan Maas and all the delegates for this keynote session. Over to you, Professor.
Thank you, Dr. Giffen, for this kind introduction. So you see, the topic of my presentation is what do we really know about the energy efficiency of buildings? So I will try to monitor a bit the real consumption of field tests, simulations, and energy certificates. All this is based on the European directives, which were launched in 2002 and then recasted in 2010, concerning the energy efficiency of buildings, energy performance of buildings. And in these directives, which are mandatory for all Europe, in the annex, the buildings are categorized into single-family homes, apartment blocks, offices, educational buildings, and other categories. So we will focus on these 4 categories, and I try to give you a summary of different research projects to characterize various building categories with respect to measurements, simulations, comfort, renovation, mechanical ventilation, and so on. So as Dr. Giffen said already, I'm a professor here at the University of Luxembourg. So what I'm going to tell you is a summary of several PhD theses which were done in the past here at our university. So I dare to say that we have today a reliable databasis to describe the situation in Luxembourg and in the greater region. First of all, I'd like to start with some definitions to make sure that we talk of the same thing. These directives go back to the primary energy. So primary energy is non-renewable energy, for example, crude oil, coal, uranium, or natural gas. So our certificates normally refer to this primary energy, which is then transformed into final energy. And the difference is you have losses during this transformation process. So from primary to final, you have losses. And what you buy, what enters the building is the final energy. That's what you pay. But the certificates refer to the primary energy. And then we have again transformation losses inside the building, which in the end we call heating demand or net energy. That is again something different. So now we'll have a look at 2 different characteristic cases. For instance, a case of electricity. So if you produce electricity, nearly 2/3 of this energy is lost by thermal energy somewhere in the production process. So if we take the case of electricity, we apply in Luxembourg a factor of 2.7 to go back to the primary energy. This is the so-called primary energy factor. If we compare then to fuel oil or gas, the factor is only 10% because we typically have only 10% of losses. So once again, European norms force us to go back to primary energy. And here you see a big difference between electricity and for instance, fuel oil or natural gas. Then the effect of climate. You know, climate is different in Europe. It's not everywhere the same. And if we look, for example, to the transmission losses of a wall, it is a U value, the transmittance, times the surface, times the energy, times the temperature difference, times time. And this factor, temperature difference times time, is not constant over the year. It changes every day. And therefore, we define the heating degree days, which is measured every year in Luxembourg and also around. In Luxembourg, it is, for instance, 3,586 Kelvin days. And this is the hatched area here, which you see in this graph. And this can be used for compensation of climate effects. So if I know the heating degree days of a specific site, I can transfer it to Luxembourg with this heating degree days. The next point are the references which we use. You can define many different surfaces in the buildings. So here in our calculation, we referred to the so-called cross area, which is simply A times B, which includes all the walls, the floors, the staircase, everything included. This surface is quite easy, can be easily calculated, but other European countries refer to the net area, which is different, or another area. So you have to convert. Here I refer to the cross area, which is, if you want to have the net area, it's 80% approximately. Just to keep in mind, other norms refer to the volumes. So you must really pay attention. What is your reference? Otherwise, you compare apple with pears. Now let's have a look on the very first result. It is the final energy for heating and domestic hot water in the years 1997 to 2007. And while you see here a specific consumption in kilowatt hours per square meter and year, the square meters are cross square meter and kilowatt hour. Just to give you an idea, 1 liter of fuel oil is approximately 10 kilowatt hours. This conversion is based on the lower heating value. Lower heating value means that the water fumes, that there is, in the fumes, there is water, and the water is in vapor form. If the water is condensed, then we call it higher heating value. That's again an important point where you have to pay attention. So what we see here is we analyzed 45 traditional houses in Luxembourg, and we found a mean value of 131 kilowatt hours per square meter and year. So that is 13 liters of fuel oil per square meter. And the standard deviation is 32. That is roughly 1/3 of it. Now the question was, are our data representative for Luxembourg and perhaps also for the greater region? So what you see here in blue, you find our sample distribution of our 54 houses, which we analyzed. And you see we put them into classes of always 10 kilowatt hours. And then you see here in blue the distribution. And we compared it to a normal distribution, which is quite simple to describe from a mathematical point of view. And okay, you see here we measured 129, which is very close to 130. So we concluded here, if the number would be a bit higher, we would have close to a normal distribution. And once we assume a normal distribution, we can say that with an N of 55, so 55 buildings analyzed, that with a probability of 95%, the mean value does not deviate more than 10 from the calculated mean value of 131. So what I want to say is our sample is representative for Luxembourg for these years, 97 to 2007. That is the final conclusion. And now, as Luxembourg is a very small country, we are used to compare to other countries around us, other European countries. But then you have to find studies where you clearly have an indication of the climate, that means the heating degree days, that you have a clear reference. Here we used cross surface, others use net, but we can convert. And also we have to pay attention that we have a comparable year of construction. Here in Luxembourg, we used from 1990 to 2007 in this study. And we found some of these studies. We found data from Germany, from Switzerland, from Austria. And when we compare to the German data, Luxembourg is consuming 30% more, or Germany is 1/3 better. The same in Switzerland. Austria is nearly the same as Luxembourg. So compared to Germany and Switzerland, Luxembourg has deficit because their houses consume more. But then we split the categories more a bit in detail. So we did not only analyze the traditional homes, we also had row houses. We also had prefabricated houses, and we had so-called low energy houses. And if we look to the average value, which we find in these different categories, we see that for the low energy houses, we only have 73 kilowatt hours per square meter and year. That means 45% less than for the traditional homes. So also in Luxembourg, we were able to build houses which consumed less energy in this period. Now let's have a look what this low energy concept meant for these years, 97 to 2007. Please pay attention, these definitions are permanently updated. So a passive house of 2000 is no longer a passive house in 2020, and a low energy house today is not a low energy house at this time. At this time, it was a heating demand of 60 kilowatt hours per square meter, including a blower door test and a thermography test. That was a definition in Luxembourg in this time period. And now if we take this 60 and multiply it by the transmission losses inside a house, which are typically 1.25, 25%, plus add the domestic hot water, we end up with 100 kilowatt hours per square meter in here. This is for net surface, and if we then convert to cross surface, we would have expected to find 80 kilowatt hours per square meter in here. So 80 would mean low energy concept according to definition, and we found 73. The conclusion is Luxembourg's low energy concept worked well. We found in our field test what was expected. And then we took data from the statistical office, which is called Statik in Luxembourg. And there we found that approximately 1,000 buildings are built here every year. But in this time, only 2% went for this low energy concept, and only 0.5% went for the so-called passive concept at the time being. That means the conclusion is, yes, the houses meet the requirements, but most of the people simply fulfill the requirements. They don't go for low energy or passive concept. They simply stick to the norm. Now we look at the electrical consumption of a family home, single family home. First of all, we look at the absolute values. So what every household is consuming. In Luxembourg, we found an average 6,000. Here you see the standard deviation. For the prefabricated homes, we found 5,400. For the row houses, 4,900. For the low energy houses, 4,800. So that means also in Luxembourg, we have considerable differences, and this low energy concept works quite well. In Germany, we find 4,100 and 5,400 in Denmark. Well, you see, Luxembourg is above Germany once again. And here are the so-called passive houses, which consume by far more. They consume 14,000 kilowatt hours per year. That's interesting. Why do these passive houses consume so much electricity? Now you see the electric consumption per square meter. And we refer once again to the cross surface. And then the picture is a bit moderated. We see the traditional homes with 24, the prefabricated 29, the row houses 28, but again, the low energy was 19. So the low energy is better than the normal one, and the passive is again above. But now in Luxembourg, we are better than Germany. So you see, if we compare to the previous slide, here 6,000 versus 4,100. But if we look to the specific consumption, we have less. Why? Because the houses in Luxembourg are typically larger than the houses of our neighbors. So you have one stove, you have one fridge, and the larger the building is, the better the specific electric consumption. So once again, we have to be very careful what we compare to each other. But still, the passive houses consume quite a lot of electricity, more than the traditional homes. And here comes the explanation. So if we go back to this primary energy, what we defined at the beginning, we have to multiply for gas and fuel oil with 1.1 and electricity in Luxembourg by 2.7. These factors are average factors for the transmission losses. They are defined by national governments. And it is not the same all over Europe. Therefore, you have to pay attention which factors are used. And here you see the blue part, that is the heat part, and the red part is the electric part. And if we look now to the normal houses, traditional, prefabricated, and series, we are around 200 kilowatt hours per square meter in year. The passive houses are considerably lower, 1/3 lower. And the passive here, this is low energy, and the passive is 50%. So the conclusion is, yes, also in Luxembourg, we were able to build houses with only 50% of the normal consumption if we apply this passive house concept. But in this case, we use only electricity because you can substitute heat by electricity. That's the reason why the European norms refer to this primary energy. So the conclusion was, yes, please let's promote low energy and passive house concept because we have a clear reduction. And then compared to Germany, for example, we are not far away. We have more or less the same specific values. So the absolute values are higher because our houses are bigger. The next question was the user influence. Because, well, this is a heavily discussed topic. What is the influence of the user? And we said, okay, let's study the user influence on row houses. So we selected from literature data where we found houses in series. So here an example, 98 houses, exactly the same, but 98 different inhabitants. This is an example from Germany. The mean value was 162. And you see, we ordered them according to increasing consumption. And the standard deviation here is shown, it's approximately 1/3. So we analyzed 15 of these row house colonies, data from literature, and we found out that the standard deviation typically is 1/3 of the mean value, which is not astonishing because it's typical for a normal distribution. And we also see that approximately 2/3 of the households are within the standard deviation interval, and 95% are within 2 times standard deviation interval. So when we now talk about user influence, we can say, okay, let's have a look. 2/3 are within the interval of standard deviation. That is the user influence. Here, this guy, for instance, is traveling all year. This is not representative. And here we have a problem with the heating system or whatever. This is also not representative. So if we look to the large amount of users, we can say the user influence in general is ±1/3. That is the conclusion of this row house study. And now we went for calculation and said, okay, select some of our houses. We selected 20 and we calculated according to a given European norm, the energy consumption. And then we divided the measured consumption by the calculated consumption. And if it is exactly the same, it is 100%. But you see, our min value was a bit below. Okay, but not far away. But still, we have here differences from one object to the other. But if we compare that with the previous slide, we find more or less the same picture. So the conclusion is, yes, there are differences, but these differences are induced by the user. And what we see here is the user influence, but this calculation is correct. So we can calculate, but we have to carefully choose parameters, the input parameters for these calculations. And if these parameters are not well chosen, we see discrepancies. And we come back to this point later. Here we did a sensitivity analysis. So we looked on some input parameters. For example, the internal gains. What is internal gains in a building? That is the heat produced by the occupants and by the electric appliances. And you can justify everything between 1.5 watt per square meter and 5 watt per square meter. Nobody can tell you which number is correct. It's depending on the user. The same is true for the indoor temperature. Typically, we choose 20 degrees, but you may also choose 18 or 22. It's depending on the user. And here is the ventilation system, the efficiency of the heat recovery of an heat exchanger in case of a ventilation. And what you see here, if you vary a bit the internal loads, if you vary a bit the temperature, you have large changes in the calculation, 20%, here 25%. And for a ventilation system, depending on the user, that means how he ventilates, if he opens the windows or if everything passes by the heat exchanger, you can have easily deviations of plus minus 65%. So what I want to say is these calculations are extremely sensitive. There are some parameters which have a large impact on the result. So you really have to carefully prepare the input data and check that they really match with what the user does. Otherwise, you will see differences between calculation and measurement. So this is, let's go back again here. That was the single family homes. I want to recall in average, we have 130 kilowatt hours per square meter in Luxembourg. And the standard deviation is 1/3. Now we'll come to the next building category, which is the schools and the offices. So we analyzed schools and offices which were built between 1995 and 2010. So let's say new schools and offices. And I dare to say, once again, compared to what was built in total, that our study is representative as well for the schools, as well for the offices. And we did again refer to the gross surface. We normalized by the heating degree days and also by the cooling degree days, because many of these offices were actively cooled. That means air conditioned. Let's have a look first to the schools. So you see, we analyzed 68 schools. And here the different colors are the different fuels which were used: gas, mazout, fuel oil, local heat network, wood, cogeneration. So different color means simply different energy vector. In average, we find 93, and the standard deviation here is 50%. Just to recall, single family homes, 131, here 93, but standard deviation here only 1/3. Here the scatter is larger. That means the building deviate more from each other. It's depending on the way the building is built and exploited. And if we look to the electricity consumption for single family homes, we were 25 or close to 30. Here we find nearly the same average, 30 kilowatt hours per square meter and year. And the standard deviation, again, a bit larger than for the single family homes, nearly 50%. And we found that canteens in these schools have a large impact on the electricity consumption. So typically we can say that a canteen adds 10 kilowatt hours per square meter of the total gross surface to the electric consumption, though these canteens are not very energy efficient. Here we see now the sum of those, the weighted sum, that we find the primary energy. You know, heat times 1.1 and electricity times 2.7. These are the official weighting factors in this time. And then we find an average of 190 with a standard deviation again of 1/3. You see, the schools in the end for the primary energy, they are close to the single family homes. They also are around 190, 200, and the standard deviation is 1/3. The best buildings are around 100, which is called green standard or passive house standard or low energy standard. But you see, the best buildings can be below 100 kilowatt hour per square meter and year. And here I marked 2 different buildings, and then you can easily understand why it makes sense to add electricity and heat. Here you see a building which is dominated by heat, and the building here, the blue part is the electricity part, is governing. So you can easily exchange heat by electricity. Therefore, here it's the same. If you compare this building here with this building here, they have nearly the same sum, but very different parts in electricity and heat. So finally, what I want to say, this makes sense to go back to the primary energy because you can exchange heat and electricity. Once again, we look to the schools, to the different building periods. Here, the first period was before 2001, then 2001 with 2004, 2005 to 2006, 2007. And we see a clear reduction in our heat consumption of the new schools. So when the schools are newer, they consume less heat. In red are the standard buildings, in yellow, the low energy, and in green, the so-called passive at the time being. But it's clear we see with age a reduction of heat consumption. But when we go back to primary energy, so you know the weighted sum of heat and electricity, we see a large scatter. So the standard ones are the red dots, the low energy, the yellow dots, and the passive buildings, the green dots. And well, you see passive houses which consume by far more than other standard buildings. And the same is true for the low energy buildings. But still, if we go for the averages, we see a difference. So the mean values for the standard is 130, for the low energy 72, and for the passive we see 35 for the heat, and then for the electricity 30, 35, 35, and then for the passive, that is the weighted sum was 1.1 and 2.67 for the primary. Primary for normal standard schools is 200, for low energy 170, and for passive 130. So you see we have a potential of reduction of 1/3 if everything would be passive. If everything would be low energy, we have a reduction of 16% in average. Here we compare again to our neighbors. I don't want to go in detail, but this is the heat consumption. And here, if you don't know, that is a flag of Luxembourg here, which I put over these columns. So these are the Luxembourgish values, and these are values of older schools of our neighbors, other European studies. And we see for the heat consumption, which we see here in this picture, Luxembourg is always below the neighbors. So our new buildings, our new schools are better with the heat consumption than our neighbors. If we switch to electricity, we see exactly the opposite. Our new schools in Luxembourg consume by far more electricity than our neighboring countries and their older schools. Why that? Well, new schools use more canteens, new schools use more computers, new schools use more ventilation and cooling and air conditioning, and all this increases the electricity consumption. So it's very clear in future, if we want to reduce, we have to have a close look on the electricity consumption. And here is the weighted sum, the primary energy. For these buildings, again, the comparison was a neighbor. And then you see that the new schools in Luxembourg normally consume even more than the older buildings in the neighboring countries. So please pay attention to this electricity use, because the tendency is very clear. We replace heat by using electricity for higher comfort, and that's a problem because the total energy efficiency does not really decrease with age. The next categories are now the offices. So once again, schools are, let's say, more or less close to single-family homes. Now the next category are office buildings from the years 95 to 2010. And we find an average value for the heat, 130. The schools were 93, the single-family homes were also 130, so not far away. But we see a larger scatter. The scatter was here 30%, here we have nearly 50% of standard deviation. And again, the different colors are the different fuels which were used. This is local heat network, cogeneration, gas, fuel oil. And we also see here for the electricity, higher values. You remember electricity for schools and single-family homes, roughly 30 kilowatt hours. For the offices, we see 170 kilowatt hours. That means more than 5 times more than residential buildings, which indeed is a big problem. Caused by computers, by cooling, by climatization. I will explain that now. Here you see the specific electricity consumption of new offices. This part is fully air-conditioned, which are nearly all, 90% are fully air-conditioned, and only a small part, nearly 10, were not air-conditioned. So for the air-conditioned, we find a mean value of 70. For the fully air-conditioned, 215. So we see a factor of 3 when we go for air conditioning. And in red, you see the offices with large data centers, computer service rooms, which consume a lot. And here you see the primary energy, that is a weighted sum of heat and electricity. The green building standard is 100. So the target is 100. And you see the heat part, the red part, is quite low. So for these office buildings, what is really dominating is the blue and green part. Green is primary energy used for cooling. Some of these buildings have special counters that you can separate, others not. Therefore, we don't always have a green column. But what is clear for these office buildings, the absolute dominating part is the electricity. And we have mean values of 700 kilowatt hours per square meter. That is 7 times more than it should be or could be. You know, again, schools and single family homes were, the traditional ones were 200, but here we are at 700. If we compare to those administrative buildings which are not actively air conditioned, they are far below. So this air conditioning seems to be a problem for the energetic consumption. Now we compare once again the financial sector with the normal administration. In the financial sector for the heat, we find an average of 150, whereas in normal administration 100. So 50% more in the financial sector. And it's even worse if we look for the electricity consumption. In the normal administration, we have 80. In the financial sector, 210. That means a factor of 3. So this financial sector, the banks, which are here in Luxembourg, they have high requirements for comfort. They have large data centers, and they have large glazed envelopes to give transparency, at least the picture of transparency. Therefore, many of these banks have glass on their facades. And this all leads to high consumption. Here we compared different facade types. When we have less than 50%, we call it punctuated. If we are between 50 and 70% of glass on the facade, we call it banner facade. And if we were above 70, we called it double glazed facade. And if we look to the heat consumption here for the punctuated, the banner and the double glazed, we see a clear increase of heat consumption. The more glass we put on the facade, but even more pronounced is the rise in the specific electric consumption. So the higher the share of the windows on the surface, the higher the electricity consumption in average. So if I would like to summarize what has to be done to get an energy efficient school and an office building, it's very clear. We should not do active cooling. We should go, for instance, for passive cooling by night ventilation. Here we see an example. This is a new school in Luxembourg, and 1/3 of the window is split into 2 parts. A smaller part is barred, and the window can be left open overnight. Nobody comes in, but still we have a high air exchange rate overnight. It's very simple, but it works quite well. This is what we call night ventilation by opening of the windows. Next, we should limit the window size. We should not have more than 45% of the building envelope with windows. Here is an example. Here you see a bad example where we have roughly 100% of windows on the facade. We should select a low G value, but a high tau value. Tau value is the percent of light which passes by the glazing, but only the visible part of the light. You know, visible is between 400 and 800 nanometer. The G value is a complete spectrum of light, including infrared and ultraviolet. And you can buy glass today with a factor of 2. That means tau is twice as high as G. This is called solar glass, a little bit more expensive, but not dramatically. And this helps you a lot, especially in these administrative buildings. We should go for daylight sensors. Here we compared two lighting systems, an old system and a new system, and we switched every week between the old and the new, and we compared 1 year in an office room, both systems. You see the old system, which is switched on at 8 in the morning, and then it's a complete day full working, whereas a new sensor, here you see the sensor, that is a new system, it was dimming according to the sun. So when we have daylight, sunlight, the new system automatically reduced the power. You can buy that today. It's a bit more expensive, but not tremendously, but you can save a lot of energy, especially in office buildings, with these daylight sensors and presence detectors for the light. And you should go for external sun blinds at the outside. And there are new systems which try to reflect the light to the back of the room. This also helps to get a high daylight coefficient at the back away from the window. That's also interesting. But of course, the sun blind should be outside, not inside, because if it is inside, then the heat is already in, and then you have to do active cooling. What else? We should have high inertia in the buildings. Here you see an example. The concrete is directly accessible. Why? This helps to avoid overheating. It gives high thermal inertia. The overheating typically takes place in the afternoon at 2, 3 o'clock. Then the temperature raises, but if you have a high inertia and high thermal mass, it heats up slowly, and then you have time overnight to relieve this heat again. So high thermal inertia is good for night ventilation and helps to avoid active cooling. Here is a comparison and a summary of what we have seen so far for the schools and offices. It is the primary energy which is shown. In red are the schools, which have an average of 190, and in blue are the offices. And we see a very large scatter for the offices. The worst offices are above 1,000 kilowatt hour per square meter and year, which is not very good. So these offices were all new. Now we made calculations and tried to find out how sensitive different parameters are. So we started with a south-oriented office. And here you see the number of overheating hours per year. So the hours of above 26 Kelvin. That was defined here in our study as overheating. And you see, if we go for an optimized building with passive means, without active cooling, we only have in our simulation 1 hour of overheating per year. That means completely negligible. But this means an optimized building. Then we changed the ceiling and we went for a suspended ceiling instead of a high inertia concrete ceiling. Then we get 2 hours. If we use internal sun blinds instead of external sun blinds, we get also 3 hours of overheating. If we don't have dimming for the lights, we get 9 hours of overheating. If we increase the size of the windows up to 63% of the surface, we got 10 hours. If we used other class, 0.5 instead of 0.35, we got 20 hours. And if we didn't have night ventilation, we got 35 hours. But still 35 hours in 1 year is not tremendous, knowing that a year is roughly 9,000 hours. So that means you are in an ideal building, in a well-designed building with passive cooling facilities, and you simply take out night ventilation. But when you start to accumulate these effects, that means you start with the optimum, and then you do the suspended ceiling plus the internal sun blind plus the dimming plus, and then you end up with 5,000 hours of overheating. That means 2/3 of the year you have overheating in this building. This is tremendous. This building has a very bad indoor comfort, and you can no longer stay in this building. You will go for active cooling, for air conditioning. And this destroys your energy balance. What can be seen here? Here we simulated these effects. So in a well-designed building where everything is fine, in an office building, we can live with 150 kilowatt hours per square meter and year. And now we simulated the individual means, and then in the end, we come up with 600. These values were found in our experimental study. So it's no problem to simulate what we found in the field tests. But it's what I want to demonstrate is this is a very non-linear effect, as we also can see here. So we start very slow. If you have a good building, you can do 1 or 2 mistakes or whatever. You can change a little bit. The building is tolerant. But if you start to accumulate all these errors, then you end up with a catastrophic value and you have to go for active climatization and cooling. And this destroys your energy balance. That's what we can also simulate. To summarize all this, I compared the primary energy of old and new buildings. Because next we will, so for the single family homes, the old ones were around 300, the new ones 220. We had 25% of reduction, and the best ones were here. For the apartments, the same picture, 25% of reduction, the best ones were here. For the schools, 280, the new ones 25% less, the best ones were here. But the offices are different. The old ones were at 280, the new ones at 260, the best ones were here, and the new fully air-conditioned are around 700, which is really not acceptable, but that's what we see in field. So that is the study about schools and offices. The next chapter is about retrofit. And I do not want really to explain you all details because we are running out of time, but we analyze typical retrofit measures and try to find out whether this makes sense from an economic point of view. Therefore, we assessed typical things, exchange of windows, for instance, insulation outside of the building, and asked the question, does this make sense? Can the user save money by investing in these things? Therefore, you need to predict the energy prices, and then we calculated the net present value, which is the money you save or the money you lose. And I simply want to go for the summary, which we will see here. So what is highly economic is the insulation of the attic. If you have an attic which is not insulated, please insulate it. It's cheap and it helps a lot. If you have a plaster outside a building which is damaged, then before repairing the plaster, please add a thermal insulation, a composite system. That also makes sense if the plaster is damaged. But if the plaster is still fine and you don't need to do anything, then from an economic point of view, it does not make sense. If you have an old heating system, a low energy heating, and you want to replace it by a condensing boiler, only because you think you can save money, it is not really economic. It depends a little bit on the age, on the conditions. It can be refundable, it can be economic, but not as much as attic insulation. What does not make sense is to exchange the windows. If the windows are still intact, if they work well, and you have a single glazed windows, then from an economic point of view, it does not make sense to exchange it. Neither the insulation of the basement ceiling from below is also too expensive to be refundable. Heat pumps depend a little bit on the size. Sometimes it makes sense, sometimes it does not make sense to exchange an existing heating by a heat pump. Now this part is about energy certificates. I started already at the beginning with this directive from EU, and every building in Luxembourg and in Europe in total needs such an energy certificate. So it was launched in 2002, it was recasted in 2010, and now in Europe we have everywhere these energy certificates, which are not really comparable. Here we did a study and we looked at these energy certificates, and some of these certificates are based on calculation. So you can calculate the energy certificate, you can calculate the energy consumption and then give the certificate. That is here the blue columns, and the red columns are the measured values of energy consumption. And you see for the buildings, the old buildings, which were built before 96, we see a large deviation between what was measured, right, to what was calculated according to the official guidelines of the energy certificates. We see 100% of deviation. When the buildings get more new, the difference decreases. So for single family homes, in total 120, which we analyzed, we saw the calculation does not match with the real consumption. And the same is true for the apartments. We analyzed 870 apartments, and we found out for the old one, we have large discrepancy, a large overestimation by the energy certificates compared to the real consumption. For the new ones, we have a convergence. And we also tried to find out why we have this discrepancy, which is described here. There are individual things which are sensitive and which are not correctly reflected in the calculation of the energy certificates. So in the end, I want to say these certificates, the idea is good, but still there need to be done improvements that they really reflect the situation at site. And the last part, which I really want to roughly have a look on, is a field study about mechanical ventilation systems. There are different systems, and we analyzed the real efficiency versus the nominal efficiency, and we saw large discrepancies. So with a ventilation system, you cannot really save energy. You can save a little bit, you can improve the comfort in a room, but you do not really save energy. And when it comes to invest, you have to say also, well, it is costing money, and the filter and maintenance is more important than the electricity cost. And the summary of the field test is that we have disbalances between the blown air and the extracted air, and then the real efficiency is below the nominal efficiency, and that you can save a little bit of energy with these ventilation devices, but not much. And if you look to the primary energy, compare the different systems, you can see if you go for a system which is running in a control loop, that means a system which automatically looks, for instance, to the CO2 concentration and ventilates only if people are in, yes, that makes sense. Then you can save roughly 50% of the energy if you go for a sensor-driven control loop system. And from the cost side, no, it does not make sense. A system without ventilation is more cheap than all the other systems. But if you compare, once again, these systems are running in a control loop and controlled by sensors, that they only ventilate when really needed, yes, you can also save 25% of money. So let's go for the summary to stay in time. We try to build up a reliable representative database for Luxembourg, and I also dare to say for the neighboring countries, for single family homes, for apartments, schools and offices. We tried to figure out what are the key parameters for energy efficient buildings and satisfied users, and economic and ecologic optima for retrofit measures. And also to check what is negative, what should be avoided. So the overall conclusion is, let's pay attention to electricity and to these HVAC technologies. First, do a good passive design. Passive means without electricity use, a good concept, a good insulation, and what helps you in summer also helps you in winter. And then you find good energy values. I thank you for your attention, and I would be happy to discuss with you.
Thank you, sir, for the excellent presentation. Now, delegates, it's open for questions. You can unmute and you can speak.
Sir, thank you for the presentation. I'm Dennis Sebastian from St. Joseph's College of Engineering. Sir, I would like to if I would like to conduct this type of analysis in our country, which all are the key parameters to keep our focus on?
Which slide? Number 8.
Yes, sir.
Sir,
asking this in India, what are the key parameters he has to?
sir, he is asking about if this type of, because you are presented the case for Luxembourg, and suppose we want to incorporate this idea in our country, in Indian,
Yes.
so we have to look into, so he is asking which all are the parameters, key parameters we have to focus while we implementing this type of analysis here.
I cannot give you a scientific answer because I did not investigate for the climate of India. Therefore, I'm a bit careful. I don't know what is the heating load and the cooling load of your Indian climate. And I guess it also differs whether you are in the south or in the north, because you are living in a very large country. But we are actually doing a similar study for African climate. So we have many students here of Africa, and we try to find out what makes sense for an African climate. And I dare to say that a good insulation and a good passive design is always positive wherever you are, because what is good for cold climate is also good for hot climate. So good insulation, in my opinion, makes sense. But the part of glazed windows and these things has to be specifically analyzed depending on your climate. Is that okay, Mr. Sebastian?
Yes, sir. It's clear.
But we can do it. If you like, we can step into such a study. We also have students from India here, and well, perhaps that would be interesting.
Sir, there is a question in the chat box. Dr. KJ George is asking how global warming is affecting the energy consumption over the years. Was it studied at any point of time?
Yeah, that is more or less the same question, because when the climate changes, the parameters change. But we are talking of 1.5 degrees for global climate change, or 2 degrees. So I guess the difference between Luxembourg and India is by far larger than what we will see in the coming years with climate change. The challenge of climate change, I guess, is something different. We get floods, we get storms, we get this type of things which are more dramatic than the change of these design parameters. That's at least what I think.
Yeah, thank you, sir. Yeah.
Hello,
yes,
sir.
Yes.
I am Ando from Jyoti Engineering College. Professor, you mentioned the need to conduct sensitivity analysis. Is it necessary for all types of houses?
Yes, what I call sensitivity analysis is we found out there are parameters where you change a little bit and you get a big impact on the final result. And we saw, for instance, for the energy certificates in Luxembourg, that we have exactly this case. They don't match real consumption. And I know also from our neighboring countries, it's not a fault of the methodology. It is just some sensitive parameters not exactly set to the usual habits of the people. So I guess it makes sense to study this sensitivity, because otherwise we do calculations, we show different effects than the real buildings. And this is not reasonable.
Okay, sir. Thank you.
Thank you.
Dear delegates, you can unmute and you can speak.
Hello, sir.
Hello.
Yeah. Myself is Sachin, and I just have a question.
Yeah.
So it goes like, how the problems of glass facades can be rectified in an energy efficient building?
Yeah, this glass on the facade indeed is a large problem. If you walk here over Kirchberg, for instance, where we have the banks, you see everywhere class, and it's clear they want to give an impression of transparency. So the opposite is true. And it's not good for energy balance. I can only tell that. No. So we should reduce the amount of class. Nobody wants dark buildings and no windows. That's not true. But there is also a well compromise, I would say, between, let's say, the percent of glass that we use on the facade. And the glass only helps you if you are close to the window. If 3, 4, 5 times the height of the building away from the window, it doesn't help because the room is dark anyway, and you need artificial lighting. So from my perspective, limit the glass and use solar glass. Don't get me wrong, I'm not saying buildings without windows, but buildings without 100% of glazed facade. That's what I'm saying. Here in Luxembourg, we found the optimum for 45%, which also depends a little bit on the shape of the rooms, depending on the size. If you have deep rooms, of course, it's different than every room is close to the window. But this is an average value, and I guess it can be different in India.
Certainly, sir, certainly. Thank you.
Thank you for the question.
Professor, I have a doubt.
Yes, please.
So you mentioned that you gave some recommendations, like we have to reduce the limit window size, we have to adopt night ventilation, all that things. Whether these studies, the results of studies is incorporated now when buildings are built in Luxembourg, whether they are incorporating these recommendations.
Are they being implemented?
Yeah, you know, we discuss with Luxembourg Ministry, but that is not so easy because there are other interests, to be very open. There are people who want to have this class, and there are people who want to sell this class, and there are handcraftsmen who want to renovate, and so on. So it is not everything fact-based on this world. Many things are driven by emotions and also by certain economic interests. But we are discussing. That's what I personally think. But once again, what is the task of a scientist? A scientist has to observe and try to be neutral and try to present what he observes. And that's, at least as we understand the role of a university and of scientists, to be neutral and to be independent of economic interests.
Very correct, sir, very correct. And that issue is there everywhere.
Yes, it is.
Yeah, it's a universal.
That is clear.
Okay, correct. Delegates, if still you have questions, you can unmute and speak. Otherwise, we will close. Or you can type your queries in the chat box. I think this actually, Professor, this is streamlined in YouTube at various, here also in our students are also, some delegates, they are also attending at different places. That is streamlined in YouTube also, this presentation. I think still no more questions, means we will conclude. I take this as my proud privilege and honor to propose vote of thanks to Professor Stefan Maas. He very clearly presented the need for thermally efficient buildings, and he cited the example of Luxembourg, and I think some of the delegates also pointed out how we can incorporate these type of analysis in Indian conditions or the local conditions. I think more study is required in that direction, but you have given some insights on the need of doing sensitivity analysis and also in one how to implement this. That is left to the people, policymakers who are implementing this. But from the academic point of view, we can give all these recommendations, and the implementation is left with them. Anyway, thank you very much, Professor Stefan Maas, for your valuable time, for sharing your knowledge with us. Yeah, it is. So it's a virtually we can, so this is as a token of our love and gratitude. We are presenting a virtual memento. Yeah. Thank you very much, Professor. Yeah. And also, I would like to thank our proud alumni, Mr. Kevin. So he is also with you. Kevin, can you come to the screen? Yeah, okay.
So
yes.
To me, and he does a great job here in Luxembourg.
Yes. So it is a great time to be with you. You are all these things. And Kevin also, thank you very much for arranging all these things. Kevin, you want to speak? Yeah.
No, it's
because
fine,
our students are also hearing, so they want to hear something from the alumni.
Yes, sir. It's my privilege to contribute between both the countries in the sense. Professor Maas does a good research over here in Luxembourg. Dr. Ashwini does a good research in India. So, if it is possible to develop a global need for the energy consumption, then it's always my interest topic. So that's what I wanted. So it's thank you.
Yeah, Kevin, you are the connecting link.
Sorry.
You are the connecting link between this collaboration.
Thank you.
Yeah, thank you, Professor. Thank you, Kevin. Okay, we'll wind up. So thank you for all the delegates who attended the session. Okay, thank you very much.
Hey, Sabro. Não.